Hello, everyone. Welcome back to Math 118. This is the beginning of week 9, and we're going to sort of dive into today what will be the major topic for the last 2 weeks of our studies. And that is this concept called matrices. The singular is a matrix, and how they talk in particular to these linear systems that we looked at last week. Okay, so a matrix um, simply, it's some rectangular array of numbers, right? Um, and we can use them to represent information, right? So say, for example, right, you're a scientist, right? And you're looking at some population of whales and you want to break down the data, right? Say you're splitting it two ways, between male and female whales, right? And then you might also split it, immature whales, your baby whales, your juvenile whales, it's with an E, juvenile whales, and then your adult whales, right? And, maybe when you're out looking at these whales, you see 15 of those, I don't know, maybe 20 of those, 5 of those, 3, we'll say 25, and 10, okay? This is a matrix, right? You can think of them as a container for information, right? It allows you to, reference two pieces of data at the same time, right? All of these are female whales, but if you want the female and the juvenile, well, then you look at that, row and that column, okay? Where this becomes really useful for us is using matrices that represent these linear systems, right? Say we have the following system, right? Say we have 2x minus y equals 5. And then we have x plus 4y equals 7, okay? And what we can do is we can put this information in what's called an augmented matrix, okay? And what we do is we have the first column represent our y values, or our x values, right? So we might have 2 and 1, right? Because those are our coefficients. In our second column, we're going to have our y values, so -1 and 4. Then we're going to draw this vertical line that's sort of going to represent the equal sign, right? And we're going to have 5 and 7, right? This is our augmented matrix that represents the system, right? So if we can find a way to manipulate these, theoretically, we can go back and use the manipulation of this to solve this system. And that's precisely what we will be doing, okay? Let's get a formal definition down, though, okay? And that's our definition of a matrix, okay? So we say an M by N matrix is a rectangular array of numbers. For us, it will be real numbers. And this rectangular array has m rows and n columns. Okay, so your sort of prototype like this. Usually we call the entries of these guys A, right? So we might have, this first one is A sub 1, 1, right? Then you might have A sub 1, 2. Then you might have A sub 1, 3, and on and on and on, all the way to A sub 1, n, right? But then in our second row, we might have A2, 1, A2, 2, A2, 3, and so on, right? And I can fill in the rest of this, A3, 2, A3, 3, right? These are all going to drop down, right, into something like AM1, right? AM2, AM3, and then we're going to get a whole bunch of dots. Right? We're continuing through all of this to AMN, right? And then we put these nice little brackets around it. Sometimes you'll see them encased by parentheses, but I think our book is pretty standard with using these brackets. And then remember, we have M rows, and we have N columns, okay? And if we're trying to represent a sort of arbitrary entry, right, you'll notice we use these subscripts, right? We might write that as something like A sub ij, right? Where I represents our row and j represents our column, okay? And so, we could ask something like, what is the dimension of the following matrices? Where here, this term dimension, right, we say that a matrix has dimension m by n, right, when it has m rows and n columns. Okay, so that said, let's take a look at a few matrices. Okay, let's say this one goes 1, 3, 0, 2, 5, 1, and then the second one maybe it goes 6, 2, 0, 5. Right. This first matrix has 1, 2 rows and 1, 2, 3 columns. So that would make it of dimension 2 by 3, right? And then the second one, it looks like it has 1 row and 1, 2, 3, 4 columns. So it's going to be a 4 by 1, okay? Let's connect this again to our linear systems, okay? And let's ask to write the augmented matrix for the following system, okay? And let's write our system down here. Let's say we have 6x minus 2y minus z equals 4, maybe x plus 3z equals 1, and then maybe 7y plus z equals 5. So we have this system, and we're interested in converting it into a matrix, okay? And so let's create a little matrix, okay? We'll have our rows represent our equations, right? And this is equation 1, this is equation 2, this is equation 3. And how many columns should we expect, right? We'll need 1 to represent our x values. We'll need 1 to represent our y values. We'll need 1 to represent our z values. And then we'll need 1 to represent the output. Okay, so it looks like we're going to be dealing with a 3 by 4 matrix, okay? And let's take a look at this, right? Our first equation, it looks like it's 6, -2, -1, 4, right, for my x, y, z, and output value. My second one looks like it has 1x, 3 z's, and an output of 1. And then it also has 0 y's, right? You can imagine a sort of phantom 0 y right there, okay? For our third one, it looks like we're going to have 0 x's, 7 y's, 1 z, an output of 5. And we're going to draw this little line right here to show that we are augmenting the matrix. The reason that we call this augmented will kind of come up a little bit more kind of later this week and the beginning of next week. But just sort of notice that, like, over here we have the coefficients, right, of these x, y, and z values. And then kind of separately over here, we have the equals, right? And this is a square matrix, which will turn out we'll see, I believe, the beginning of next week, that square matrices are very interesting and very important. Okay, so the natural question is, how can we use these ideas, like this matrix thing? It's cool, I guess, right? But how can we actually use it to help us solve these problems? Okay, and we get into something called elementary row operations. You might hear them occasionally called EROs. Okay, there are three elementary row operations, and they are analogs of the systems that we used in the last lecture to simplify our equations. Okay, they're just now written as a thing that can be done to matrices. And as we saw with looking at these equations, they will keep our system consistent. Okay, so here are the three elementary row operations. Number one, you can add a multiple of one row to another, right? Where that multiple has to be non-zero, right? We have number two, you can multiply a row by a non-zero constant. And three, you can interchange two rows. And we have three little pieces of notation to kind of keep track of how we're doing this. So if we're adding a multiple of one row to another, okay, we're going to start with row I, okay, we're going to add to it k, which is our non-zero multiple, times row j, and we're going to redefine that as row I, okay. If we're just multiplying by a non-zero constant, we can write that as k times, row sub 2 or 3 or whatever, okay? And if we're interchanging two rows, we might write something like this. Row I is interchanged with row j, okay? So here's what we're going to do. I'm going to give you a system, okay, right here. And we're going to solve the following system. It's going to be x minus y plus 3z equals 4. Looks like x will go plus 2y minus 2z equals 10, and 3x minus y plus 5z equals 14. And we're going to solve this two different ways. We're going to solve it via the traditional means, sort of on this half of the screen. And then we're also going to solve it as a matrix system. And we're going to kind of look at how they are direct analogs of one another. And hopefully it will kind of give you an idea of just a little bit of why we might prefer matrices, okay? So the first step is just going to be rewriting our system. So I am going to abuse the fact that I'm on an iPad for this, okay? And then over here we need our matrix. So let's write our augmented matrix for this system. Looks like we're going to have 1, -1, 3, 4. It looks like 1, 2, -2, 10, and 3, -1, 5, 14. Okay, so we're going to solve through this guy first, okay? And we're going to use the notation that we used in the last set of lectures, okay? The first thing that I'm interested in is clearing away out of this equation and this equation, my x and my 3x, okay? And what that means is I definitely want my top row, or my top equation, sorry, to stay the same, right? And since I don't want it to change at all, I'm going to write that one first, okay? what do I need to multiply by equation 1 to get the x in equation 2 to go away? Okay, that would be -1, right? So we're going to do equation 2 minus equation 1, okay? And then I guess we can redefine that to be equation 2, okay? And so when we do that, we're going to have 0 x's. 2y plus 1y is going to be 3y. And minus 2z minus 3z is minus 5z. And it looks like 10 minus 4 is 6. Okay. To get this one to go away, what do I need to do? Well, I would need to multiply row 1 by -3. Okay. So I guess I'll write that one over here. Equation 3 minus 3 times row 1 redefines equation 3. Okay. And when I do that, what am I going to get? Well, I'm going to get 0 x's again, right? Looks like it's going to come out to me to be a total of 2 y's, a total of minus 4 z's, and then 4 times -3 plus 14 is 2. Okay. So what happens if we're wanting to do this over here, right? Well, if we want to get this negative 1 to be a 0, we're going to actually do the same thing, right? We're going to take row 2, we're going to subtract row 1, and use that to redefine row 1, right? And it's a little bit, at least to me at least, easier here because there's less sort of junk in the way of our coefficients. We can just do 1 minus 1 to get 0. Okay, in fact, I'm actually going to copy down this first row and add my line to make it clear this is an augmented matrix. Okay, and then, well, what happens here, right? I have 2 plus 1 is 3. For my next one, I have minus 2 minus 3 is minus 5. 10 minus 4 is 6. Okay? What you can think about us doing here is following along with these matrix steps, what we're doing here, right? And so we need to get this guy, right? We need this 3 to become a 0. And how would we do that? Well, we would take row 3, and we'd subtract 3 times row 1 to redefine row 3, right? And when we do that, well, it looks like we're going to take 3 minus 3 is 0. We're going to have -1 minus 3 times -1, so plus 3. Then we're going to end up with a 2. And then we're going to have 5 minus 3 times 3, so 5 minus 9 is -4. And then for our last one, 14 minus 12 gives us 2. Okay? And notice how since these steps are the same, right, we have, this is now our augmented matrix for this system. Okay? And so when we think about what we want to do next, our first thought might actually be to manipulate this equation. But what I want to draw your attention to is this 5. It kind of makes it a little frustrating to deal with. Instead, why don't we turn our attention to this equation, right? This equation which has all of our coefficients divisible by 2. And let's generate our next one in this series with, say, 1/2 times equation 3. Our first two equations are not changing, so I'll copy those down. And then for our last one, we're multiplying by 1/2, so it looks like we're going to get y minus 2z equals 1. Okay. For our augmented matrix, right, we're going to do the same thing, right? We're going to do 1/2 times row 3. Okay. And actually, what I'm going to do for the sake of time is copy this matrix I guess I'm going to cut the matrix and then paste it again right here and change these, right? We're going to have 1, 1, minus 2, and 1, okay? We're going to go on to the next page for these. So I think I'm going to actually copy them once again and move them over here, okay? So what do we want to do next, right? Well, why don't we use this y to actually cancel this 3y, right? Then we're not dealing with any nasty fractions if we don't want to, right? So to go to our next one, we can take equation 2, we can subtract from it 3 times equation 3, okay? And so that would turn our system into what? Well, the first and third rows aren't changing, so we can copy those down. And then for our next one, it looks like we have y times -3 is -3y plus 3y is 0, which is great. That's what we wanted. Then here we have -2z times -3 is positive 6z plus 5 is just a single z. Well, that's going to be what, right? It's going to be 1 times -3 is -3 plus 6 is 3, okay? Looking at our matrix system, our first row is going to stay the same, right? Our third row is going to stay the same, 0, 1, -2, and 1. And then what's going to happen in this middle, if we're sort of following along, you know, what we did to solve our equation here and here, right? Well, it looks like we're going to take row 2, subtract from it 3 times row 3, and use that to define row 2, okay? And so then what happens with that, right? We're going to have 3 minus 3 is 0, right? We're going to have 5, it looks like plus -2 times -3, which is 6, so it's -5 plus 6 is 1. Then here at the end, we're going to have 6 minus 3 is 3, okay? And then there's one last thing to do, and that's exchange our equations, right? If we swap equation 3 with equation 2, we're going to get the following system, where I'm going to once again abuse my ability to copy paste and to move things around. We'll take this guy, move him out of the way, move that up, move this back in, and I can erase those. We have this system in triangular form, and then I can do the same thing with this augmented matrix, right, where we're taking row 2 and switching it with row 3, with the caveat that these have to change a little, right? Since we're switching, we're going to have 1, -2, 1, and 0, 1, 3, okay? And both of these, right, allow us to quickly read off our solutions with some simple back substitution, right? We'll get x equals 2, y equals 7, and z equals 3, okay? So we've seen that our augmented matrix system, we can do equivalent work to solve these systems, right? We can do similar work on that in a way that gets us eventually to the same place, right? But what's not necessarily clear is how you would do this on its own. And that idea is a process called Gaussian elimination, okay? Specifically, you're using Gaussian elimination to put your matrix in what's called row echelon form. And what's important about this idea of Gaussian elimination is that Gaussian elimination is the process, okay? And it's actually the same process that we just used, okay? But to be more specific, Gaussian elimination is the process we use, putting these elementary row operations together to put a matrix in what's called row echelon form, okay? We have a matrix is in row echelon form. If it satisfies the following conditions, okay? So these are a set of rules that hold when we are indeed in row echelon form, okay? So the first one says that the first non-zero entry, you can think of that as a number, right? In each row is a 1, okay? We can think of this as the leading entry. Is what it's sometimes called. Number 2, we have that the leading entry of each row is to the right of the leading entry of the row above it. Okay. And number 3, we have that all rows consisting entirely of zeros are at the bottom of the matrix. Okay, because remember, we can use these elementary row operations to switch rows, and so we can do that. Okay. One addendum, there is another sort of further way to do this, okay? And that's row reduced echelon form. It's often abbreviated RREF, okay? And RREF, it's all of the above, and the following condition. Number 4, every number above and below a leading entry is 0, okay? So I know that this is a little bit wordy and maybe a little bit opaque. So I have some examples cooked up for you of 3 matrices, and let's look at if any of these are in row echelon form or reduced row echelon form, okay? So let's take a look at this first matrix, okay? We see that the first thing we need is that the non-zero, like the first non-zero entry of each row is a 1. So we walk this way, we hit a 1, which is great, 1, that's great, 1, that's great, and 1, that's great, okay? So this, hits point 1, but it kind of falls apart when we look at point 2, right? Because it says that the leading entry in each row is to the right of the leading entry in the row above it. Well, this one is to the left of this one, so we failed on point 2, right? This is not in row echelon form, unfortunately, okay? Let's take a look at this next guy, right? So we walk this way, we hit a 1, we hit a 1, we hit a 1, and we hit a 0, which is fine, because there is no first, non-zero entry. It's all zeros, right? When we look at our ones, we always take a step to the right going down, and our row of zeros is at the bottom. So this is in row echelon form. That's great. Okay. What about this next one? Okay. We can see we hit ones as our first non-zero entry. Our row of zeros is at the bottom, and our ones take steps to the right. But further, take a look at that fourth criterion from the previous page, right? When we take our 1 and go straight down, we only hit zeros. When we take this one and go up and down, we only hit zeros. When we take this one and only go up and down, we hit zeros again, right? So this one is actually in reduced row echelon. So I have to fit form down there. Okay. So we've had a look at some of these candidate matrices. So it seems like it's right time to dive in and solve some systems. Okay. So let's use Gaussian elimination to solve the following system. Okay. We'll have 4x plus 8y minus 4z equals -4. We'll have 3x, once again, plus 8y, and now plus 5z's equals -11. And we'll have 2x plus y plus 12z equals -17. And one thing of note before we get started, this 4 should be positive, and that 2 should be negative. Okay. So the first thing that we're going to do is we're going to compile these into our augmented matrix, right? So we have our coefficients, -4 and 4, 3, 8, 5, -11, -2, 1, 12, and -17. Okay. And if we remember the rules that our row echelon form has to follow, our leading entry on each row has to be a 1. Right here I see a 4. It's a problem. But I can fix that rather easily, right? If I just multiply row 1 by a 4th, right? First thing I'm going to do, always, is copy down the rows that aren't changing, okay? That is going to minimize the little errors that sort of tend to pop up, right? It's when you're doing these sorts of calculations, it is easy for those little calculation errors to come up and bite you because there are these little things, right? But if you make sure that when you're copying the rows that aren't changing, you're less likely to make those, okay? But so now we have this, right, where I just divided each of these by 4 to get these entries. And what happens next, okay? Well, the leading entry of each row needs to be to the right of the leading entry above it, which means that if this is the leading entry of the first row, both of these need to be zeros, okay? So how can I get them zeros? Well, when I'm trying to manipulate them into a 0, we're going to use the other rows and add multiples of them, okay? So our first row is not changing, right? So that means I should write that one down, right? 1, 2, -1, 1. And so then what next is going to happen to my other rows? Well, to get this 3 to go away, I should take row 2, subtract from it 3 times row 1, and then use that to define row 2, right? So we're going to have 3 minus 3 is 0. We're going to have 8 minus -6, right? 2 times -3 is -6, for a total of 2. Next, we're going to have 5. It looks like plus 3 for a total of 8. And then in our constant row, it looks like we're going to have 11 minus 3 for a total of negative 14. And I guess this guy can get moved a little closer. For our last row, how are we going to get rid of this negative 2? Well, I can take row 3, and I can add to it 2 times row 1, okay? And then use that to redefine row 3. When we take a look at that, we're going to have negative 2, looks like plus 2 to get a 0. We're going to have 1 plus 4 to get a 5. We're going to have a 12 minus 2 to get 10. And then it looks like we're going to have 17 plus 2, or rather negative 17 plus 2 for negative 15. Okay, so what happens next, right? Well, so we have these zeros, right? And it looks like the next thing we need to do is make sure that this row follows the right rules, right? For this one, we need our first non-zero entry to be a 1, which right now it's a 2. So what I can do is I can multiply row 2 by 1/2, right? Then I'm going to get the following matrix, right? My first row doesn't change. My last row doesn't change. And my middle row gets divided by 2. 0 divided by 2 is 0. 2 divided by 2 is 1. 8 becomes 4. Negative 14 becomes negative 7. And I'll redraw that bracket. Okay. So again, the next question is, well, what happens now? Well, once again, we need to make sure that the leading entry of each row is to the right of the previous one. So we need this entry to become a 0. Okay. And so what I'm going to do is I'm going to use this entry to clear this entry, or rather this row to clear this entry. Okay. And the way that we can do that is we can take this and we can, copy down our first 2 rows because they're not going to change. 0, 1, 4, negative 7. And then now that we have those 2, right, what do we need to multiply by? Well, we need to take row 3, and we need to add to it. It looks like we're going to do negative 5 times row 2 to redefine row 3. Okay. So what's going to happen? Well, 0 plus negative 5 times 0 is, well, 0, right? We're going to have 5 minus 5 is 0, which is great. That's what we wanted. We're going to have 5, looks like minus 20. It's going to be negative 10, right? Then we're going to have 15, looks like plus 35, right? Negative 15 plus 35 comes out to 20, okay? If I multiply row 3 by negative 1 over 10, we're going to get exactly what we wanted. 1, 2, negative 1, 1, 0, 1, 4, negative 7, 0, 0, looks like 1, and negative 2. Okay. I'm going to copy this guy onto the next page for you because we've actually solved our system now, right? Because what system of equations does this represent, right? This gives us the system x plus 2y minus z equals 1. Looks like it's going to be y plus 4z equals negative 7, and z equals negative 2, right? This is a triangular system. So what we can do is we can back substitute, right? We can take z equals negative 2. Well, then y is going to be negative 7 minus 4 times negative 2. which comes out to 1. We're going to have that z looks like it's 1 minus 2 times 1 plus a negative 2 comes out to negative 3, right? So we get, just to write this down, x equals negative 3, y equals 1, and z equals negative 2, okay? And we did this manipulation, again, through matrices, and then, pulled this out the other side. But I want to show you something a little bit interesting about this, okay? And that is why we would care about row reduced echelon form, okay? So here's our example. We're being asked to put the matrix 4, 8, negative 4, 4, 3, 8, 5, negative 11. If this matrix sounds familiar, it should. Negative 17. We're being asked to put that into RREF, okay? Well, by the previous example, I guess I'm not numbering them, so we'll just say previous example. We know the following thing, right? We know that that matrix, right, which is this guy, is equivalent to this one. So what I can do is I can copy him and bring him over here, okay? And let's put this in RREF and see what we get, okay? If you remember, the defining property of RREF was not just that it had these zeros, but everything above and below the other leading entries was 0 as well, okay? So that means we need to get this guy to 0 and these two to zeros, okay? And so we'll do these sort of one at a time, right? Why don't we try and clear this 0 first, okay? So why don't we do, looks like we're going to take row 2. We're going to do that in green. We're going to take row 2. We're going to subtract from it 4 times row 3, and then use that to redefine row 2. Okay, I got a little big, so I will shrink them down so that we can fit. Okay. So which rows aren't going to change? Well, number 1's not going to change, and number 3 is not going to change, so we can just copy those down. But what happens here in row 2? We have 0 minus 4 times 0 gives us a 0. We have 1 minus 4 times 0 gives us 1, right? And then it looks like we're going to have 4 minus 4 times 1 for 0. And then we're going to have negative 7 minus 4 times negative 2, which is going to come out to 1. Okay? And now that we've cleared this 0, or this entry, and turned it into a 0, let's keep going and let's try to get that one to go away. Okay? So let's do row 1. Looks like it's just going to be directly plus row 3 to redefine row 1, right? Because if I just add these two, I get 0. So what's going to happen now? Our second row is going to stay the same. Our third row is going to stay the same. And what happens to this row? Well, we have 1. Looks like we're going to do 0 plus 2 is going to leave a 0, right? And 1 plus negative 1 is going to leave a 0, which is great. And then negative 2 plus 1, well, it looks like that's going to come out to negative 1, okay? Before this is an RREF, we have one more manipulation to make. We need to turn this guy into a 0, okay? And how can we do that? I guess we'll go straight down here in the interest of space. Well, we can take row 1, and we can subtract 2 times row 2 and use that to define row 1, okay? So what's going to happen here, right? As I've said a number of times, and I will say every time that I remember, let's write down our rows that aren't changing, okay? And then what's happening to this first row? Well, we have 1 plus 0 is 1. We're going to have 2 minus 2 is 0. 2 zeros gives us 0. And what happens here? It looks like we have -1 minus -2 for a -3. Okay? And here's what I want you to notice here. Okay? What system does this represent? Okay? When we turn this into a system again, well, we're going to have x plus 0y plus 0z equals -3. We're going to have y plus 0x plus 0z equals 1. We're going to have z plus 0x plus 0y equals -2, right? That's the power of going all the way to RREF, is it allows you to simply read off your answers because they're just right there, right? X is -3, Y is 1, Z is -2, okay? You don't need to trouble yourself with this back substitution if you take your matrix reduction a couple steps further.